Hello, good morning to everyone. Yes, I'm Andreas from Imperial College London. Now I'm in my fourth year, so finishing my PhD. I will be in the University of Warsaw from the new year. And I'm going to talk to you about this work we've been doing with my supervisor, Artu Rayanti, and in collaboration with Tommy Markkanen. We're looking at the Higgs vacuum metastability topic in this cosmological context. So I'm going to walk you through a little bit what we've done in our first paper and now in our upcoming paper that should appear in the archive very shortly. So yeah, in contrast to the other two talks, we're starting from a more particle physics kind of territory and then moving into cosmology. So from the standard model perspective alone and the parameters that we measure, we are seeing a couple of interesting things. So first of all, we can see that the standard model on its own can remain valid up to high energy scales, where we would like to consider PSM effects or some other high energy effects. And that is, again, an internal point of view of the standard model. It's not external, not from the other data that we have, but from the theory itself, you don't have any problems extending it and running it to higher energies. You can see an illustration of it in the Higgs self-coupling lambda. So as it runs with the energy scale mu, it doesn't have any discontinuities or any funky behavior, just smooth function to higher energies here. And that in principle, that can mean that in principle, you can use the standard model at these higher energy scales. Of course, this is with a lot of caution. It's not something that you can advise strongly. But in principle, you can use it at the higher energy scales, and you can make this connection with the early universe where you had these high energy scales in order to construct a consistent minimal model to describe the early universe. And still, again, from the kind of parameter motivated discussion, for the same reasons, you see that for most of the values of lambda, as it runs with the energy scale, at some point it turns negative. You have these different colored bands that denote the uncertainty in the measurements, but for most of these colors, you see lambda turns negative. And then that means that if you have your usual Higgs potential, which I've written here, you have your quartic coupling. If lambda turns negative, then that means that when you have your Higgs potential, which I show here, with the non-zero vacuum expectation value, you have here at the origin, you have this Mexican hat potential that we know from the Higgs physics. But if you turn negative, when lambda turns negative, you develop this potential barrier and you develop a second deeper vacuum state. And because we're dealing with quantum fields, right? The Higgs field is a quantum field, then that means that you can always tunnel through the barrier or go over it or have a combination of both. So that renders the current vacuum that the Higgs resides in to be a metastable one, not an absolutely stable one. Of course, as I said, you have some room within the uncertainty to recover absolute stability, but the central values place you in this metastability region. And here I'm also showing, because we're now talking about curved spacetimes in the early universe, so I'm hinting that we will be considering the effect of curved spacetime. So I'm including this term that is coupling the curvature, so the Ricci scalar with the Higgs field here, and the strength of the coupling comes from this non-minimal coupling psi, and this is what we're trying to constrain with this type of studies. And one important aspect of this is that this psi is the last unknown renormalizable parameter of the standard model. You cannot probe it with accelerator experiments. Space-time curvature is very small today. So with this cosmological type of study that I'm gonna show you, you can obtain orders of magnitude stronger constraints on psi. Okay, so what happens when you have this decay process? So that the moment that it happens, you have this nucleation of vacuum bubbles, as it's very familiar terminology in this type of literature. So you have the decay happening at a specific point in space-time. at random, but it's one point, and then it excites the surrounding space-time around it. And effectively what you see from your point of view in the false vacuum is that you have these spherically symmetric bubbles that have the true vacuum or something strange going in. Could be a singularity, could be something that you need quantum gravity to describe. You don't really know, but you have this exotic physics within the bubble, and you are in your false vacuum universe on the outside. These bubbles very quickly reach an expansion speeds that are close to the speed of light. And because they are very energetic processes and you have all these exotic phenomena on the inside, they devour the surrounding space-time, and it's very catastrophic for our false vacuum perspective. And because they travel so fast at the speed of light, you won't see them coming. So it's not a very pleasant scenario to consider. And quantitatively, how you can study them is through their expectation value. So it's just the product of the decay rate of the process per space-time volume, the decay rate for the process to happen, times the space-time volume, and you're integrating over your past light cone. And the reason that you're integrating over your past light cone is that because the universe is still in this metastable vacuum, it hasn't decayed through its cosmological evolution. So that means that we can place this quite firmly, this constraint, that no bubbles should have been formed in the entirety of our past light cone. Otherwise, they would already have grown because they expand so fast, and they would already have reached us. And the connection that you make with the expectation values when you are quantifying this a little bit more robustly. So you're saying that the probability that you have 0 bubbles forming in your past light cone should be significant enough of order 1. Where now if you are applying a quantum probability distribution, you're talking about rare events. So that's how the expectation value comes into place. And from this argument, you can place this constraint on the expectation value, which effectively means that you shouldn't have bubbles in your past light cone. So we don't have to worry about it today in flat space. If you do the calculation, the decay rate is very small. So you can go on with your day. Vacuum decay is not going to happen anytime soon. But the point is that in the early universe, you could have significantly higher rates. And that is kind of the point of doing this cosmological status of vacuum decay, because exactly you have to account that the vacuum state has managed to survive until today. And this is the way that you can allow you to constrain parameters for your physics. So specifically, we're looking in this early universe scenario of inflation, when we had some talks about it, so I don't need to spend a lot of time talking about it. So during inflation, this is kind of the master quantity that we will be using, this expectation value for the bubbles. And during inflation, we can express it like this. So you have still your decay rate, and the rest of the terms have to do with your space-time volume. Now we're looking during inflation, so we're integrating over the e-foldings of inflation. This is just a variable that counts how much inflation is taking place. N equals 0, it's at the end of inflation, and start is at the start of inflation. From observations, we are minimally assuming 60 foldings, which is the minimum that you need to match with observations, but it can last way longer than that. So yeah, all of your cosmology comes into place in this cosmological quantities. Your particle physics come through gamma, and then by imposing this constraint, you are constraining the last remaining unknown parameter in here, which is psi that I showed you before, right? And which enters the calculation through gamma, as I'm going to show you in a while. So again, a little bit for the basics of what is going on. So for this double well potential that I showed you, very famously, from the late 70s and 80s, you have these classical solutions that are called instantons, or these tunneling processes. So in our case, that we're again looking during inflation, curved space-time scenario, you have these high Hubble scales. So the Coleman-de Lucia instanton, which is way more complicated, approximates the Hawking-Mons instanton, which is much simpler and easier to deal with. And the bounce action that characterizes the Hawking-Mons instanton is given by this quantity written in terms of the Ricci scalar. And this delta V now is the height of the potential barrier. So the value of the Higgs potential at the top of the barrier minus the value at the false vacuum. So here, so this is the barrier height, and the reason that the height comes into the calculation is because the Hawking-Moss bounce is a classical solution. It takes you over the barrier. It doesn't take you through with tunneling, and that's why only the tunneling, the height comes into the calculation and not the width or something else. So when you have Hawking-Moss instanton, then you can approximate your decay rate like this, and it's given in terms of your bounce action. And this is how Xi will come into place, right? Because you have your Higgs potential. And already, because we're talking about this quantum field theory of the standard model on curved space-time, you have curvature effects entering already at 3 level, exactly through the non-minimal term that I described. So you cannot really deal with it in any other way. Of course, we want to be more precise, and we want to include more terms, and we want to include curvature corrections and so on. So you have a much more complicated version for your potential. Of course, we can simplify it a little bit to make our lives easier. So you have these extra terms that arise by having these loop corrections, going to higher loops, and you have so your loop correction now, you can see here, it's going over all the 31 degrees of the standard model. So you have, quarks, leptons, ghosts, and so on. And your usual loop correction now, you have also, it is of the essence that you have this curvature correction in your loop correction, because you're doing QFT on curved space-time. So you have this thing which is not there in your flat space-time calculation. And these curly m's as well correspond to its degrees mass, effective mass, but they also include the curvature correction there as well. So this is also important and fits with the topic of this workshop. And there's a couple points here. First of all, because again of the high Hubble scales that we are dealing with in this regime, we can safely omit the dimensionful couplings. These first 3 terms, these provide an RG flow fixed point when if you set m equals to 0. So you can disregard those and simplify your life a little bit. And then what else you want to do is do this process called renormalization group improvement, where you want to get rid of your renormalization scale dependence in a consistent way. And this, what you can do is that you choose mu to be a function of the field and the curvature, mu star, in such a way that the loop correction will vanish explicitly. So if you solve this equation equals to 0 for mu star, you obtain a numerical expression for mu star, and if you plug this into your potential, then you get this RG improved effective Higgs potential. You have disregarded the first terms, and now you have your quartic term, your non-minimal term, and you have this extra term that is always radiatively generated. It's a minor correction. It doesn't affect your the behavior that much, but you cannot get rid of this, and you have to calculate this. And this is kind of the overview of how you do this calculation, and especially in the first paper, this is where it kind of finishes. So then you have this, again, kind of an overview of what is going on. So you have a potential for your Higgs. You want to calculate the height of this the potential barrier because you need to plug it into your decay rate. Then you have to calculate the other cosmological quantities that you have in your integral, and this is subject to the inflationary model, which I haven't mentioned so much. So in the first paper, we dealt with quadratic, quartic, and Starobinsky inflation, but it's just at this level, at the potential, nothing more rigorous than that. So you just plug in your potential, you do your calculations, and so on. You plug in everything into your integral, and then by imposing this constraint, you can get this lower constraints on psi. And of course, if you look a bit, the quality of your results, you can obtain some implications depending on when exactly the bubble production happens. But it's not now to connect it with the recent paper that we're working on, and maybe with a more cosmological discussion. So if you're, as we heard, if you want to go and do Starobinsky inflation properly, it's not enough to, it's not like you're just plugging in the inflationary potential, you are including this R squared term in your Jordan frame of your action at the beginning, and then you're doing this conformal transformation and everything. So here is just very quick overview. We don't have to worry about the specifics too much. You start with the action that you have your Einstein-Hilbert term that gives you general relativity. You have the non-minimal coupling between the Higgs and the curvature, that's fine. and you have your Higgs field with the quartic term, and then you have this R² term that Starobinsky added in the 80s. And this can appear naturally like these higher order terms that you can have in your reaction. And if you go through this process of conformal transformations and field definitions that you do in this type of work, then you can canonically diagonalize your Lagrangian. You go to the Einstein frame, you recover Einsteinian gravity, general relativity. So you have your usual term, but now you have this addition in the matter sector. You have an inflaton field that drives inflation, but this has arised naturally. You don't input it by hand. And then you have the Higgs field, which now we call it rho because we ran out of letters. So you have recovered your inflationary potential. So this is characteristic Starobinsky inflation, the potential. But now you have some extra terms appearing in your Higgs potential. So what used to be just psi r for the quadratic and lambda for the quartic, now you have these extra terms that come in these respective terms. You have some higher order corrections, and the appearance of these extra terms will play a role on these constraints and these cosmological implications that I mentioned in the previous slide. So now we can see a plot that has kind of all of these considerations together. So y-axis is exactly these psi values, the lower constraints. So these shaded areas in this parameter space denote the disregarded area of the parameter space. The white one is the one allowed. And we're showing this in terms of the value of the top quark. Again, because it's a data motivated standard model calculation and the top quark has the largest uncertainty in the measurement. That's why we're giving it in terms of this. So here at the central values, we denote them with this orange area. So if you don't go through the rigorous implementation of Starobinsky inflation, if you just use it the potential, then you obtain this blue bounds that I show you here. So you get something like roughly 0.06 at the central value for psi, which is still pretty good if you cannot constrain it with accelerator experiments. But now if you're go and be a bit more careful and you implement Starobinsky inflation a bit more carefully, then you are jumping to almost 0.13, 0.14, which is much stronger. Of course, here you see two different shades of this purple bounds, and the reason for this is we're showing those with a different definition for the end of inflation, because what is going on actually when you're playing this game is that now bubble production is enhanced during the very last moments of inflation, and that is where things start to break down, because you have some amount of de Sitter approximations that may render your results a little bit not trustworthy. So if you are a bit more conservative with how you define the end of inflation, you can trust your results and maybe get this lower bound at 0.1 more or less. And you have some extra features here in the plot that kind of limit your parameter space, which are a bit more technical. Of course, we can talk about them if you like. But yeah, the point of this plot is that you have managed to disregard, let's say, confidently this area of parameter space, and then this white area, and possibly this is allowed. And maybe I can just go to conclusions now in order to show you what is, to recap what is going on. So we consistently include this loop curvature corrections beyond de Sitter for the Higgs potential. So this QFT of the standard model on curved background, you have accounted for that. You are obtaining this stricter lower psi bounds because you have these additional negative terms that arise in your Higgs potential in Starobinsky inflation if you do it rigorously. So this is the comparison from before. There's this brief comment that you have bubble nucleation towards the very last moments of inflation. I haven't showed you any plots with that. I have some, so we can talk about it. And this is kind of a big point. So you have some breakdown of your de Sitter approximations, and it becomes of the essence that you need to start considering dynamics of reheating and these effects to this calculation if you want to still claim accurate and definitive bounds. And there's also these minor points here, which again I haven't talked about them. They're present in in the plot. So you are approaching this conformal point where psi is 1/6, where is the limit of the Hawking-Mohs instanton. So you also may lose some validity if you're going too close to that point there. And there are similar hints against eternal inflation in both studies. It doesn't really depend if you're going rigorous or not, because you get an enhanced bubble production at the very early times. But this is very preliminary, and it's not something that you can claim with absolute certainty. So I'm gonna leave it here, and I'm very happy to get questions. Thanks very much.
Okay, thank you for this very interesting talk. So now it's time for questions, and I see that Gerardo has one. So Gerardo.
Hi, thanks for this wonderful talk.
Sure.
I wanted to ask you, is there any situation in which this kind of instantons, this bubble nucleation that you consider could be relevant for, I don't know, collider physics? Like, do they have an imprint on particle production in the LHC or something like that?
I don't think so. I think the effect is minimal. Yep.
I'm asking because, there was a time when it was very popular to consider this kind of production of black holes and all that, which is in collider physics. So I don't know if there is a situation.
Yeah, as far as I know, the effect is minimal. And that's, like the point is that you want to go in these cosmological scenarios that are very more extreme and exotic, because that's the only way that you can have significant enough coupling between, for example, the Higgs and curvature, so that the effect is visible. So I think there's been also works around when you are considering vacuum decay in the presence of a black hole, for example, when you have significant space-time curvature. And you have some enhancement of vacuum decay there, and this is very big part of work of Ruth Gregory and her collaborators. Which you need to have some extreme black hole. It's not, and it has to be a black hole. It doesn't, if it's like something smaller, like a neutron star, the effect will still be very minimal. So even neutron stars have extreme gravity scenarios compared with terrestrial standards, still the effect will be so minimal that you won't be able to see anything. So it's something that I guess we're only limited to cosmological scenarios or maybe some extreme black hole cases. But other than that, probably is you can go on your day and you won't never see it happening.
Okay, thank you very much.
Yeah, sure.
Okay, I have a small question. It's a bit technical.
Sure.
Can you repeat why you choose this mu star as your
Yes.
scale? I mean, is it only because it is convenient, or is there any physical reason?
So you want to get rid of the normalization scale because it's unphysical, so it shouldn't be there, but of course it comes in because you have to naturally through the calculations and how the dependence on the energy scale comes into. So there are different ways, and of course it's like you have to make a choice to how to get rid of it. So a very popular in literature is you just get mu equals h. So the scale is the Higgs field. And if you're doing flat space calculations, that's very good. It's sufficient enough. But when you're going into this curved background scenarios and you don't include the effect of curvature, then you're kind of disregarding the leading term in what should have been there in your scale dependence. So then there are some, again, approximations that we can have like a linear combination of the Higgs and the curvature, let's say H plus R, for example. But if you do this, then, and if you want to include loop corrections, then you have to include your loop correction. So this mu star is exactly canceling this, and because now you have such a small loop correction that now it vanishes, it justifies it as a valid expansion. And now you consistently can disregard your loop correction because it has vanished with this mu star. So like taking care of those both things at the same time. So you've gotten rid of your normalization scale dependence, and now your loop correction has vanished exactly. So you're omitting it when in the full calculation, and you're not getting an uncertainty from this point. So that's, but you can make other choices as far as you are consistent, then they should be fine. But this is, depends on how accurate you want to go. So because this is actually a tricky thing to solve numerically, if you cannot get consistently a numerical solution, then you have to do something else. So I think it comes with the problem depending on the limitations of the specific problem that you have to solve.
Okay, I think Antonio has a question or comment.
Sure.
Antonio.
Yes, yeah. Thank you for the talk. So it's more a question about so because you used a specific type of inflation model. My question is, if you get to really understand the whole process of vacuum stability of the Higgs and everything, could this be then possible to use it for all the possible models that are still out there and just use it as a restriction, as for example nucleosynthesis is used, and because you, of course, you don't want this vacuum instability. So in a future, could you use it to see which models do not have these vacuum instabilities and which do have it, and all of this kind?
So, okay, yes. So there are some extra plots that I haven't showed. And so one point that has to do with this is that with this blue line, I'm not showing here just to make the plot clear, but you have two other overlapping lines because we considered quadratic and quartic inflation, and you have almost degenerate results. And that comes from exactly how you're treating things in your calculation. So if you have high scale inflationary potentials, you are kind of getting this behavior here that is denoted by the blue one. So you cannot differentiate easily between them. So that's one point. If you have something that is vastly different, like low scale, or I don't know, like a multi-field that does some funky stuff, maybe there's potential power that you can differentiate between them, but it's not something that enters the calculation too explicitly. So if you have like a range of Hubble scales that you're considering, then like it won't really, like the metastability won't care that much. It will just be the values that your potential will have, for example, here. So it doesn't see it that much. It sees a curvature correction. Okay, fair enough. Where the choice of the inflationary potential matters is when you're doing this calculation, and it comes indirectly, for example, for the Hubble rate and conformal times and everything. Then this other point about eternal inflation, which you may be able to disregard and differentiate with, comes exactly, again, I haven't showed this, it's in the first paper, it comes with from the point that you get some enhancement of vacuum decay at very early times. And if you had eternal inflation, you would get these extra additional bubbles at a very early time. So you can kind of say, okay, maybe this is unphysical, I don't expect this to happen. But of course, this is not done yet in a rigorous eternal inflation model. So it's not something that we can claim with validity. So I think apart from maybe those extreme cases when you're crudely separating different inflationary scenarios, I think to use it as a tool to go through inflationary scenarios, you cannot pick them apart too much, apart from the very separate categories, because you're losing some power into the specifics, because exactly that it's not like the potential of the inflationary model enters the calculation super explicitly. There is a dependence, and so again, this I haven't done the full calculation, but I wouldn't expect it to be able to be so strong so that pick one or two inflationary models that you say, okay, these are the realistic ones that still comply with that. But maybe in large chunks you can talk about them.